Hello and welcome to a lesson on integration by substitution. In this lesson we'll work through 7 examples of integration by substitution, 5 of them for indefinite integrals and the last 2 for definite integrals. And we'll cover a whole range of different types of substitution which crop up on A-level papers. To begin then, let's integrate 2x plus 1 multiplied by x minus 3 to the power 4. Now we could do this by expanding the x minus 3 to the power 4 using the binomial expansion, but there would be a lot of work involved. So let's see how a substitution can make the problem far easier. And what I'm going to do is let u equal x minus 3. And you'll see why in a minute. Du by dx, the differential of that, would be 1. If I differentiate x minus 3 with respect to x, I get 1. Now it turns out that we can treat that very much like a fraction and split it into du is 1 times dx. So du is equal to dx. And that enables me to swap the variable u for the variable x. Now what I'll also need is to know what x is in terms of u, because I'll need to substitute it in this bracket here. So we can see here that x, take the minus 3 the other side, x will be u plus 3. So let me write down that x is equal to u plus 3. And now I'm in a position to change the variable here. I'm going to integrate. What would 2x plus 1 be? Well, x is u plus 3. So 2x will be 2u plus 6, and the extra 1 there will make that 2u plus 7. X minus 3 is simply u, so x minus 3 to the power 4 is u to the power 4. And the dx can be replaced by the du. Now at first glance you might think we're no further forward, but this is a lot simpler to integrate than this expression here. Why? Because I can multiply the bracket by the u to the 4, and I get 2u times u to the 4 is 2u to the power 5, plus 7 times u to the 4 is plus 7u to the 4. Now I've got 2 polynomial terms in u that are very straightforward to integrate. Integrate the first one and we get 2u to the power 6 divided by the new power, 6, plus 7u to the power 5, raising the power by 1, divided by 5, the new power, plus a constant of integration. Now the u was my invention, it wasn't in the original question. So I need to now substitute back for the u and replace it with x minus 3. And while I'm on, I'll cancel 2/6 to 1/3. So this will be 1/3 x minus 3 to the power 6 plus 7/5 x minus 3 to the power 5. Plus a constant of integration. And that completes the question. Example 2. Integrate x over x minus 2 with respect to x. Now before designing a substitution for this question, let me show you how an expression is far easier to deal with if it's got 2 terms on the top and 1 on the bottom than if it has 1 on the top and 2 on the bottom like this. So let's consider numbers to start with. What if we had 2 plus 3 divided by 6? Let's compare that with 6 over 2 plus 3. Well, 2 plus 3 over 6 is 5/6. But that is exactly the same as 2/6 plus 3/6. So we can split something like this by just dividing each term on the top by this single denominator. 2/6 plus 3/6 is equal to 5/6. This, on the other hand, is more complicated. 6 over 5 is 1 1/5. Notice we can't do something like this. We can't split it into 2 because that would be 3 whole numbers plus 2 whole numbers, which is certainly not 1 1/5. So this substitution I'm going to use here is designed to make the bottom a single term. I'm not worried if I introduce an extra term on the top. Right, let's get back to our problem and say let u equal x minus 2. So du by dx, if I differentiate that, will be equal to 1, which means, as in the last example, du is the same as dx. Now I will want to know what x is in terms of u, and you can see here if I take the minus 2 to the other side, that's right, also x equals u plus 2. Now the integral will become the integral of, instead of x, I've got u plus 2, and instead of x minus 2, I've simply got u. And the dx is replaced by du. So I've now got an integral with respect to u. And I can split this by saying u divided by u is 1 plus 2 over u. And now I'm in a position to integrate this with respect to u. So the integral of 1 with respect to u is just u. The integral of 1 over u is log u. So the integral of 2 over u is plus 2 log u. And we'll have a constant of integration. And now we need to replace the u by the x minus 2. So that gives us x minus 2 plus 2 log. Now x minus 2 should be put in modulus signs because if it's negative you can't have the log of a negative number, so it's the log of the modulus of x minus 2 plus c. And finally, because c is any number, it can incorporate the minus 2 as part of it. So I can write my final answer as x plus 2 log the modulus of x minus 2 plus c. And that concludes example 2. Example 3. Integrate x multiplied by the square root of 3x minus 1 with respect to x. In this question, it's the two terms under the square root sign that cause the problem. If we change that so we have u to the power of half, in other words the square root of u, it's much easier to deal with. So the substitution that we're going to use is let u be whatever's under the square root sign. In this case, 3x minus 1. So du by dx is equal to 3, which means that du is 3 dx. This is different from the previous two examples where du was equal to dx. Now over here I can see a dx on its own, so let's take this one step further and get dx on its own by dividing by 3. So we'll get dx is 1/3 du. We'll also need to know what x is in terms of u. So from this equation here we can say that also 3x is equal to u plus 1. So x is u plus 1 all divided by 3. And now we're in a position to carry out the integration. We can say that this is equal to the integral. The x becomes u plus 1 over 3. This is the square root of u, which is u to the power of half. And then the dx is 1/3 du. So we'll write the third at the front, 1/3 du. Now the denominators here, 3 times 3 is 9. Let's take 1/9 out the front of the integral. And then left inside we'll have u plus 1 times u to the half. U times u to the half is u to the power 3 over 2 plus 1 times u to the half is u to the power of half. And that has to be integrated with respect to u. So that gives us 1/9. If we integrate u to the 3 over 2, we raise the power by 1, we get u to the power 5 over 2, divided by the new power, 5 over 2, plus, integrate u to the half, we get 1 more than a half, u to the 3 over 2, divide by the new power, 3 over 2, plus a constant of integration. Now to divide by a fraction, we turn upside down and multiply, so this gives 1/9, and this becomes 2 over 5 u to the power 5 over 2 plus 2/3 u to the power 3 over 2 plus c. Now I'm going to multiply the bracket by 1/9, and while I'm doing that I'll also change the u back to 3x minus 1. So our final answer, 2/5 times a 9th is 2/45, and then we'll have 3x minus 1 to the power 5 over 2 plus 1/9 times 2/3 is 2/27, 3x minus 1 to the power 3 over 2 plus a constant of integration. So it's not a very elegant answer, but it is the answer to this integral here. Example 4. Integrate x multiplied by the square root of x squared minus 1 with respect to x. Now this example looks pretty similar to the last one, but there is a subtle difference, and that's why I've included it. Again, we've got two terms under the square root sign, and to get that to a single term, I'm going to let u be what is under the square root sign. So let u equal x squared minus 1. So du by dx is equal to 2x. The differential of x squared minus 1 is 2x. So du is equal to 2x dx. Now where this differs from the previous example is I don't need to find x in terms of u, because the x is going to be used up by this substitution. So I can see I've got an x dx, so let's manipulate this so I have an x dx. In other words, let's divide it by 2. X dx will be a half du. And now I'm ready to carry out the substitution. This is equal to the integral, that is u, the square root of u is u to the power of half. The x dx is simply replaced by a half du, so we'll put the half at the front, a half du. And we can integrate that. That will give us, let's take the half outside the integral, and we get integrate u to the half, we get u to the power 3 over 2 divided by the new power plus a constant of integration. So that's equal to a half multiplied by, to divide by the fraction, turn upside down and multiply, 2/3 u to the 3 over 2 plus a constant, and here the 2's cancel, I'm left with 1/3 u to the power 3 over 2 plus a constant, and finally replacing the u with x squared minus 1, we get 1/3 x squared minus 1 to the power 3 over 2 plus a constant. And that's what we find with substitution. Sometimes with something like this, we'll need to express this in terms of u, but other times the substitution that we make will actually use that up as part of the relationship between du and dx. And that concludes example 4. Example 5. Integrate 6 sin x cos cubed x with respect to x. Now the kind of substitution we try here is we look at the trigonometric function that's raised to a power and we let that trigonometric function be u. So in this case I'm going to say let u equal cos x. Then du by dx, differential of cos x, is minus sin x. So du is equal to minus sin x dx. And if we look across here, I can see I've got a sin x dx. So let's get sin x dx explicitly, and it would be minus du, just divided by minus 1. And now we're ready to complete the integration. We've got the integral of 6 cos x is u, so that's u cubed, and then the sin x dx is minus du, so I can put the minus sign at the front and du. And now it's straightforward. If we integrate minus 6u cubed, we get minus 6 u to the power 4 divided by the new power 4 plus a constant of integration. And now I'm just going to replace the u by cos x and simplify the 6 over 4, and we'll get minus 3 over 2 cos to the power 4 x plus a constant. So a fairly complicated integral ended up with quite a simple answer. And when we put the u equals cos x in there, again we found that the sin x was used up as part of the substitution relationship between du and dx. And that concludes example 5. For our final pair of examples, we look at definite integration using substitution. Example 6. Find the integral of 1 over the square root of x plus 2 with respect to x between the limits of 0 and 1. To begin, we want a single term under the square root sign. So we're going to say let u equal x plus 2. So du by dx will be 1, which means du is equal to dx. Now what we're going to do is change the limits of this integration so they apply to the variable u, and that will mean that it's not necessary to come back to the variable x after we've completed the integration. So let's change the limits. When x is equal to 1, that implies that u is equal to 1 plus 2, which is 3. And when x is equal to 0, that implies that u is equal to 0 plus 2, which is 2. And our integral now becomes the integral from 2 to 3 of 1 over, now x plus 2 is u, so we've got the square root of u, which is u to the power of half, and the dx is simply the same as du. Let's rewrite that as a negative power to make it easier to integrate, so it's integrate u to the minus a half with respect to u. And that gives us, raise the power by 1, we get u to the power plus a half divided by the new power a half, and that's between the limits of 3 and 2. And that's equal to divide by a half, multiply by 2, so we get 2 u to the power a half between the limits of 2 and 3. And now if we substitute this in, remember u to the power a half simply means the square root of u, and so that gives us 2 times the square root of 3, substituting the 3 in for u, minus 2 times the square root of 2, putting the 2 in for u. Now we could work that out on a calculator and give it to however many significant figures, but in a pure maths exam it would be perfectly acceptable to leave the answer like that. And now our final example, example 7. Integrate 3x e to the 2x squared dx between the limits of 0 and 2. Now this is the first exponential function we've come across to integrate using substitution. The one thing we do know how to integrate is e to the u. The integral of e to the u is simply e to the u. So that's our starting point. Let's simplify this so we're looking at e to the u. So let u equal 2x squared. So du by dx is equal to 4x, which means du is equal to 4x dx. Now let's see if we can sort of match this up with what we've got here. Here we've got 3x dx. So let's first of all get x dx by dividing by 4. So that will be 1/4 du. And then I could multiply that by 3, so I've got 3x dx is equal to 3/4 du. And now I'm going to change the limits. We're looking at x going from 0 to 2. So when x is equal to 2, that implies that u is equal to 2 squared is 4, multiplied by 2 is 8, so u is 8. And when x equals 0, u will be 2 times 0 squared, which is still 0. So changing the limits and changing the variable, our integral becomes the integral from 0 to 8 of, now e to the 2x squared becomes e to the u, and then we know that 3x dx is equal to 3/4 du. So let's put 3/4 at the front, du. And we can bring the 3/4 out the front of the integral as a constant, and then we're just looking at integrating e to the u. But when we integrate e to the u, we simply get e to the u. And that's between 8 and 0. So that gives us 3/4 e to the 8 minus e to the 0. Well, e to the 0 is 1, so we can give our final answer as 3/4 e to the 8 minus 1. Again, we could work that out on a calculator, but often a pure maths exam will say give an exact answer, and that will be the exact integral to this question here. Now that concludes this lesson on integration by substitution. We've looked at a range of different substitutions, but what have they had in common? Well, if we've had a bracket to a power, or more than one term under a square root sign, we've looked to simplify that. Whatever's in the bracket, let u be equal to that. Whatever's under the square root sign, let u be equal to that. If we're looking at a trigonometric integration, let u equal the trigonometric function that's raised to a particular power. If we're looking at an exponential integration, let u be whatever power of e that we have. You'll now find an exercise with 7 questions, and each question corresponds to each of the 7 examples we've just been through.